How long is the snake? We just did it last time. With a huge square root inside of the integral. Now work. Okay, people who like physics, you have to help me with this for this week, because do make mistakes, and it's not my specialty. Biology, microbiology, that's my specialty. And math, obviously, but not physics. So make sure you check I don't say something weird, and then fix me if I do. You don't have to copy this, but this is in your notes. Work is the energy produced by a force, F, pushing a body along a given distance, D. The force, if force is constant, the work done has a formula, and put this formula in the box. Write this down. W equals F times D. F is the force pushing a body with a distance D. And let's give you work. Work. There's lots of things we need to review for this, and I don't appreciate it too much because it's a calculus class, not a physics class. So either it's boring for people who know physics, or it's too confusing people who don't know physics and don't like it. None of it is very necessary for this chapter. We just give you basic. But for you to remember is, so what is the units, international units for work? How do you say this word? Joule. Because I used to say joules, but then people told me it's wrong, so it's joules. Okay. Then force is what? Newtons, good job. Pushing body in meters or feet or whatever is given. In American system it says it's in foot, pound, you see? Yes, and then guess exactly what I said. If you have force multiplied by, so we're multiplying force by distance. You don't have to copy that either. But the idea is I'm pushing this chair again. A little bit of force for this tiny distance, a little bit distance, and maybe a bit more, maybe a little bit less. The sum of this will give you that. The sum of all those tiny forces times tiny distances gives you the work. And then you sum all those works, that gives you integral. Write this down. Work in total work, will be integral, and you integrate force times dx. Dx, those are tiny distances. Make sense? So it's a force, so huge today. This is force, and then dx is the tiny distances collected together, tiny distances. Force times distance gives you work from A to B, lots of work from A to B. That is the idea. Make sense? So in this chapter, we're going to learn several cool things. One of them will be about springs. Hooke's law. Do you know anything about Hooke's law? Not from the Peter Pan, Hooke's law, but the other one. So topic 1, springs. Springs. And then we're going to do pumping water and other liquids topics. With the springs, we need to know the definition or the idea of Hooke's. Wow, that's very thick. Hooke's law. Surprisingly, even I remember this name. So, from school, I do remember this name from school. Hooke's law is f of x equals k times x, where k, so let's put this in the box too, that's the most important here. Same shape, to be honest, just a little bit different idea. K is a constant for spring, so we're working with the springs right now. Spring, and I'll explain in a second what it means. And then f of x is force to keep the spring in its shape. Force to keep, yes, I'll show you how it stretch or shrink. To keep the spring. And then I'll continue the sentence in a second, but I can hear the discussions, which means it needs some kind of explanation. So spring, let me show you this. Looks like this. Say spring is attached to one side of the wall or ceiling, doesn't matter. This is the spring. It's a 3D object, but to be honest, it's just, you can always find the length of the spring. You guys recommended last time to make it flat, but we don't want to. Now we know how to approximate the length of it without making it straight, using integration. So, and formulas we introduced last time. This is the spring in its normal position. If I want to squish it, it becomes like this. And by squishing, I mean compressed. That's the official term. So the force, when I'm pushing it, I'm using force. Duh, because it's tiring, right? So I know I'm using force. So to keep it compressed, or what else can I do with a spring? Stretch it. So let's do that. I will put it here because I don't have space, but you put it somewhere you want. If I want to stretch it, I drag it, and it also takes some effort to do. So I will do stretched. Stretched. But stretched how? And now it's important where x is coming into the picture. You see this x? X function depends on x. So how? X units beyond its normal length. X units. What did I show you last time that all my sizes are so huge? I got excited. All my pencils have a very thick size. X units beyond. So either it is shirt off, if I'm compressing it, right? Shirt off. Or if I'm stretching beyond its natural length. Its natural length. And I don't need a negative sign here. I only need x to be new minus old in the absolute value. New minus old, like so. So I will check what was the original one. Then I check the new one. Take the distance, and I like, okay, it's 5 inches off. I don't need to be -5 because I'm shrinking. I just know that it's 5 inches off the original size. What do you think about this? Does it make sense? This is a spring problem, which actually I enjoy more than the other problems because I can visualize it easily. Stretching or compressing, and then how much force it takes me to do that. Here's some visualization, which I already showed you, so you don't have to copy this. But different ideas here. Natural position of the spring, then there's x is 0 because we did not change anything in its size. That's it. Then there's no force. Then force is 0, and so on. Now, when we are shrinking, there will be a distance, so x will be negative. X is in the absolute values, actually, not really. But positive or negative extension or shrinkiness. That is the idea. And then you see either you do it or you put some object on it, mass, with some kind of mass. Here's the problem number 1. A force of 6 pounds is required to keep a spring stretched. Very interesting. So if I know how much force it takes me to keep it stretched, then find the work done by this force. What is the work done? Again, people who don't like physics too much, we usually question, why do we need those problems in this class? Answer number 1, this is calculus for engineering, that's why, deal with it. that's what I think, because I don't big fan of it either. But answer number 2 is, every time you build a car or any kind of mechanism, you don't have infinite number of work in your hands to use. There's no infinite number of energy to be used for something. So you need to calculate how much work is done to send the rocket into the space, to use the shuttle in the space. And you need to minimize this work, usually, because you don't have infinitely of it. So that's why we know how much pressure it takes us to keep something stretched or shrinked, or to send something against the gravity to the space. Now I know how to calculate the work done, and I want to make it as minimum as possible, so I don't. And it's also very expensive, pricey in general, not only money, but how we use energy. So I want to make sure it's optimal. While I was talking, did you copy the problem? Good job. A force of 6 pounds is required to keep a spring stretched 1/2 feet beyond its normal length L. Find the work done. So Let's write down the formula. The work done is integral from a to b, f of x dx. So I will have f, which is force, dx is times the length, right? Times the distance, and then you collect them all from a to b. Where, in this specific case, f of x is k times x. Again, we know different formulas for different scenarios. Fighting gravitational forces. This one is fighting the resistance of the spring. In some springs, we have barely any resistance. If it's silicon spring, it kind of still pushes it back, but too easy. Or some of them will be so hard, you barely can change the inch of it. So K is this constant for specific spring. K is the constant for any specific spring. And usually it's at the end of the physics book. If the spring is aluminum, it's one thing. If it's rubber, another thing. Silicon, another thing, and so on. So let's figure out what we have. We have the 6 pounds. 6 pounds is the force. So F is 6. We don't have K, and we don't have any information about the spring material. But we have the information how much it's keep being stretched or compressed. It is stretched by 1/2. So I'm multiplying by 1/2. And now I can find K. If I know how much force it takes me to stretch the spring by 1/2, from here I know how much work. No, I can calculate the constant of that spring. How resistant the spring is coming from this equation. Does it make sense? K. Finding K. K is 12. So this is the resistant constant for this specific spring. We don't even know the material of it, but now we know it's K12 resistant. K12. Interesting. There is no dogs involved, but 12 resistance. Now, that was step A. Step A, we found K. Step B, we found K using specific information for specific timing. It takes me 6 pounds to keep the spring stretched 1/2 feet beyond its normal length. How much work is done in general? Then I will put this information into integral and collect all of the other forces together in the integral. That will give me work. Work is the integral, f of x dx. F of x is 12k. We found k, but for all types of different distances, not just 1/2, 1, 0.7, and so on. dx. 12, thank you, yes. Good job, you see I'm checking if you're paying attention, as always. 12x. X is from what to what? Yes. How much do we, so for you to understand, let me explain this too. Normal, and then we're stretching it. When I'm stretching it, I'm not just magically jumping from this state to this state. There's some kind of process on the way, right? Every piece of this spring changes. Next piece, here it is, changes. Next piece. This is literally what slicing is about. We're slicing into tiny distances, and now we're putting some work to stretch each of them. Each of them will have this delta x, which is change in length, right? And now I'm done. From where to where I'm done? What do you think? From 0 to 1/2. Do you agree, disagree? Ideas, comments? How did you know? Bless you. How did you know it's from 0 to 1/2?
Because when it starts in its normal position, it's 0,
Mm-hmm.
it stretched out to
1/2 additional work, exactly. So 1/2 feet or inches or meters were additional. So we need to figure out how much each piece, slice, was changed from 0 to 1/2. We need to put work or effort for each piece, not just magically from one state to another state. Make sense? Very interesting that we're literally moving all of them. All of those tiny pieces are being moved by stretching them. So they're changing location. Whatever used to be old delta x, now it's going to be bigger delta x. And we know by how much. So from 0 to 1/2 is a total thing. That is pretty easy to integrate. So 12x squared over 2, that's 6x plus 1/2. It becomes 6/4, which is 3/2. Let me move it to the bottom. 6/4, which is 3/2. And now units are important. And I will not claim that I understand that really well. I kind of do finally, but it took me forever to figure it out. What are the units? Joules. And then do you know how they were created?
This one's in
Feet, right? And?
it's a foot-pound.
Foot-pounds, exactly. So foot-pounds, LBS, since there are many. Okay, foot-pounds, which is joules, right? Do we all agree on that? No? Yes? Okay, see, that's what I'm also concerned. So is it joules then or not? Oh, joules and in kilograms, that was saying. But I guess it doesn't really matter. I see. So you see in this thing which I found, they say in the American system use foot-pounds, so joules have this. Okay, so they can be actually. Yeah, that confuses me as a foreigner as well, right? But you see, they say here, joules can be used in pounds, in foot and pounds. Yeah.
The problem gave us units.
Yeah, exactly.
We can't use joules unless we convert.
Yeah, we convert basically. Exactly. You both are right, but you convert basically. So interesting, but I ask people who work in the field, what are you using if you're in America? And everyone still use meters. Because when you publish articles, it will be officially accepted by international journals. So it's all in our measures, which are meters and kilograms. So then what's the point to even bother? Anyway, so that's just interesting conversation I had with people in biology and engineering. Bless you. Feet per pound. Do you know why I'm so picky about this right now? Because I actually like how it makes sense. So we have number of weights. So pounds are how heavy this object is. Either the chair I'm pushing or a spring I'm stretching, or I'm pulling the rope with a bucket, right, to get my water. So it has weight. And weight is not a total weight. Not total weight of this thing. It's a weight of every piece, which this is where infinitesimals are come in. Infinitesimals, many pieces added together, right? Infinitely tiny pieces. And then we have size of each, right? So it kind of makes sense to me somehow that heaviness times how long it is gives you work, joules. How much work it takes me to work on this object. Push it, stretch it, pull it, explode it, I don't know. So you know what I mean. Something fun. So what do you think about that? And this is my explanation. From the original one, we stretched 1/2 more. Questions, ideas, suggestions? What do you think? Yes?
So are joules the same as foot-pounds?
Yeah, it's actually here. I also don't know, so I'm always honest about it. Physics, it's not my specialty. But I found this article, right? That's what I do as a scientist. I don't know, I Google. And this article says that indeed joules are in feet times pound in American system, or meters times kilos in every else system. Thank you, though. The question is good, yes. So yeah, maybe write it down if you need it. I will not be picking up any of this on any exams because I'm picking about the math part. But in your physics classes, if you ever take any engineering classes, they will be picky about this. So we were asked to be consistent. So let me know if I ever messed up with units. Make sure you tell me. Not too bad, people. That's my favorite topic, actually, about the spring, because I understand. And the Hooke's law is just fun. Now, second topic of this chapter is the most long one. let me see, do I have a spring here? Okay, pulling something with the rope. That was the picture too. But now we're gonna do pumping water problems. So pumping, not water specifically, but liquids. Pumping liquids, or basically pool problems. How much work it takes to pump something. And that's what we're going to be torturing you for the couple weeks, then exam too, and probably final exam as well. Pumping some liquids, pool problems. Basically, from all possible problems about work, they had to make a choice which one to put for this class in the book. And they chose a spring, and I also saw pooling buckets, which is pretty interesting because gravity works differently. If the bucket is the very end, it's kind of easier already to pull it. Why? Yes, so you're pulling a bucket with water from the, what's the name of that thing? Well, what? Well, yes. So you're pulling it. Why it's so hard at the beginning, but then it gets easier later when you pull something? Why do you use less work at the very end? Yes. Few what? Less distance to pull, which means why? Why it matters? Why do you use less force? It does, it feels easier, but why? Yes. There's a weight on the rope. You also have to take into account not only that, so the higher it is, the more the gravity pushes it down, but the rope is heavy itself. So at the beginning, you have to pull all the rope first with the bucket. And now all the rope is behind you, so the bucket only left, and it's very easy. So it's pretty cool. These infinitesimals are not equal. When I'm pulling the spring, it also seems like to be not easy or hard the same way, at the beginning or at the end. Same when you're pulling a bucket with the water. With the pool, we will have a different formula. The pool, the work done by pulling out or pumping water out from the pool or tank is integral from A to B, rho G A of Y. We will be doing dy case mostly. D of Y dy. Yeah, it looks beautiful, I know. Let's put it in the rainbow box to make you feel better. Rainbow box. What? Rho. Oh, you don't. Okay, see. Thank you for letting me know. Yes. Rho is RHO. That's a new letter. You will see it a lot. It actually has lots of constants in and so on. In this specific case, rho is reserved for density in physics. In math, we use it different ways. But in physics, and don't worry, I'm writing it down. It's actually in my notes. Don't forget to tell people what rho is. Rho, RHO. It's a nice circle with a tail. It's density in physics. Density, just a second. For example, we're not always gonna give you water, but it will be popular. For water, the density is known as 1,000 kilograms, in kilograms, per meter squared. And then you convert it to your stuff, whatever you want. Yes? Yeah, it's a very smart comment. It's a Greek R, rho. In Russian, we say ro, because you guys don't have the sound. Well, people who know Spanish, they have the sound. Ro. I have a friend with a baby, and when I meet her baby, I always tell her, and I think he gets scared every time. She's like, I don't know, what's such a weird reaction? It should be fun, but he gets scared. It's so bad. I think he doesn't like me now. G, guess what a G is? How did you guess? It is gravity. Why it's important to have gravity? Because we're pumping them water up. Whatever was on the floor is lifted up. That means the gravity will be resisting meter per second squared. And those are usually just given, you know them, you check them at the end of the book. And together it gives you weight. So weight of the spring we used before, or weight of the rope with the bucket of water, that's one thing. But this is the weight of the liquid. Chocolate will have different weight than water. Water has different weight than oil. So density is important. In more complicated problems, viscosity matters. When you're pumping honey out of the container, it's a completely different problem because honey also has different viscosity. So it's pretty cool how they use the applications. But the most important for this class is what the heck is A of y and what is D of y. And this is where books are not consistent. So my job is try to explain different cases. The A of y is consistent. That is a cross-section area. That is a weird A. Area. A is area of the horizontal slices. We are slicing our 3D object horizontally. Horizontal slices of the tank. We're lifting each slice up, so we need to know what shape of it. If it's a circle, if it's a square, if it's a star, and that's gonna be the area. A is the area of that. D says distance to lift. Distance to lift. We can lift just above the edge of the tank, or we can have a fountain. But also maybe there's only half of the tank is full. Now there's more space to lift. But also maybe the fountain is twice larger than the pool. If we're creating a fountain, then the work will be done to do that is larger. And now the most inconsistent part in different books, and you will see it definitely between your physics class and our class, is what is A and B. That is because this problem can be done in different ways. These two things can be kind of interchanged a little bit, and the answer will be the same. You just need to understand what is happening. So either it is the height of the, let me see, just to be consistent with the first book first. Either it is the height of the water, or sometimes it is the height of the tank. So let me do first. They call it vertical extent of fluid. So let me just write it down in plain English, which is height of fluid. Oh, they call it fluid, not liquid. What's the difference between fluid and liquid? Anyway. Or, so slash. You also will see sometimes the height of the tank. I will be consistent with the first one, but some students submit in exam the second way and they give them full credit. So that is fine. I did not know it at first, so I took points off. Then they explained me this is how they taught in physics classes. I checked with other people. It was correct, and then I actually understood it later. It is correct. So I will be teaching one way for people who are not into physics. But if you are, you should check out both ways, and you'll see how awesome it is. Both ways are pretty cool. This is the introduction of the formula. Ideas, questions on this? Any additional information you want to tell people, so I tell people? There are definitely people in this class who likes physics. I can see your eyes, face expression. So do you want me to add something which I don't understand? Let me know. This is your time to shine. Like you should tell me. If not, let's do the first example. And then I will finish it on Friday. On Friday, I will do more examples, so it makes it a bit easier. But what we want to do is, let's zoom in. We want to do this classical example we're doing calculus 2. Find the work needed to pump something out of something. And needed to pump the water. It's usually all water, so they don't say half of it or something. The water. So let me see. I will do 6 meters. Yes. The water, 6 meters. Everything is in meters. Yes. I'm choosing my way to do it. So obviously we like meters more in my class. Out of. The shape of the tank is crucial. So this is where I will highlight it at some point. Cylindrical tank. cylindrical tank or pool with the given height, and it's not 6, it's 10 meters. Oh, so it's not full of water. Then they gave us the radius of the cylinder, which is 5 meters. And then they say we want to pump it 15 meters above the bottom. The water is pumped 15 meters above the bottom of the tank. Above the bottom of the tank. Not yet. Almost there. Almost there. 5 minutes earlier. So, check this out. That's going to be lots of wording in this chapter, so just letting you know. But you need to imagine the shape first. I see the cylindrical tank, and without reading anything else, I will try to just illustrate the cylindrical tank. I know how the cylinder looks like, and if you don't Google, you'll find out. The cylinder looks like so. It's a right cylindrical tank, so it's not tilted, it doesn't shrink. It looks like a typical tank, like so. Then I see another information about it. It has height 10. Okay, so measurements, it's 10 of the height of the tank, and radius is 5. So I take the center and I know it is 5. Okay, interesting. And then I want to illustrate the water situation. So take another color or pencil. See, it says the water is only 6 meters high. So it's not full. Here it is. This is the water illustration. 6 meters. And then there's a 15 number over there. What does this do? What is about 15? Guess. Distance from the bottom, but the tank is 10 meters high. So what is happening after 10? There's a fountain by 5, exactly. 5 meters extra. And I'll just illustrate the fountain, but it doesn't have to look like this. The point is, I now know the height of the water that we need to be lifting, each piece of water. And when I say piece, that's actually the most crucial part. What we're doing here is what we did in 7.2, slicing the 3D object. We're slicing it. So let me show you the sample slice. Here's a sample slice. The sample slice has some width. This is sample slice of what? It's not, I don't care about the shape. I don't care about the pool. I care about how the water looks like. Of water or liquid or fluid, whatever that thing is. And now I want to figure out how much work it takes to lift this piece of the slice of water or any liquid. So let me do fluid because it can be different, right? Fluid. And now I notice the shape of it. Not only I know the width, that gives me the case. What case is it, dx or dy? What do you think? dy, how do you know? We actually don't even have axes here, axis of x and y. So I will have height, and I will put conveniently the tank on the floor, which is not always the case. We will have a pool below the ground, and it's going to be up to you to choose. Is it going to be below x-axis or above? In this case, I figure it's kind of convenient to put it on the floor. And then I see that the width of each slice can be described as dy. Don't you see it? So the projection of this width goes to the y-axis. So it's going to be dy. Now, what is the area of this slice? That is going to be in the formula. Let me put it here. Area. Since the slice have what kind of shape? Circle shape of A. Then we know that it's going to be what? Pi r squared. That's just a coincidence. It matches with the first example we had for discs and washers. because we were slicing it like ninjas with discs or rings. In another example, it can be a triangle, it can be a square, it can be a rectangle, and you already had this idea before. What if tank looks like a beautiful star shape because it's a fountain with different decorations? Then the slice will be a star, and your job is to figure out the area, no matter what, because you're engineers and physics major, and I always make a joke, computer scientists, I don't know, good luck. Like, we'll merged with other people, just figure this out. In this case, it will be simple. Pi r squared with given radius, with given pi, we do that. But then the weight, so we're going to do times width of it. That gives me volume of each circle. Volume of each circle will be area times width. Integrating the whole thing means lifting, and that's the last thing I wanted to say, lifting each piece up, imagining you're actually lifting it up like so. But piece will be on a different height. The piece at the very top will travel the least. The piece at the very bottom will travel the most. And that's where integration comes in, from 0 to what? From 0 to how high the height will go. And then the more we're lifting it, the more work you have to use to do it. Pretty cool. And we're going to finish it next time.